Okay, yes? Okay, awesome. We are online. Welcome everyone to the class. Here is a couple of things we are going to do today, and then to the rest of the quarter. So the plan will be that today I will be talking about evolution of networks and how do you think about dynamic networks and how do we model that. Then next week we will also have one more kind of a more traditional network science topic. Then I think on Thursday is the exam, if I remember correctly, right? Tuesday. Okay, great. So then the exam is on Tuesday next week. Okay, great. So exam is on Tuesday next week. Thursday next week we'll do the one more kind of the classical network science topic, most likely about robustness of these networks and so on. And then for the last 3 lectures, we will kind of move towards the representation learning on graphs and deep learning as well. And we'll have a series of 3 lectures on knowledge graphs, applications, and some theoretical properties of graph neural networks. And those lectures will be basically given by the postdocs and students in my group or prepared by them, because that's kind of latest, greatest there is in this area. So I think it will be super exciting. So that's essentially the plan for the next 2 weeks, and then it's end of quarter and kind of Merry Christmas and all that good stuff. All right, so that's the idea. So what are we going to talk about today is we'll talk about evolving networks, right? Networks that change their structure over time. Essentially, almost all the real-world network evolve by basically adding and removing links and edges over time. And there's many examples like this in social networks, right? We make new friends and we kind of lose touch with the old friends. People come into the network, people leave the network. You can also think of the internet, web graphs, emails, phone calls, any kinds of communication networks as networks that evolve over time. And one way to study them is to create these types of snapshots and look at the network structure over time. There are many other examples. For example, this is an example of a collaboration network in a class like ours. After homework 1, homeworks 1 and 2, and then after the class project, right? And again, you see kind of visually in this case that this network is getting more connected. Here, nodes are students, and edges between the nodes exist if there is a reported collaboration, right? So given our collaboration policy, we could actually map out this network for this class. It would have around, I think, 350 nodes, and then some number of connections. Okay, and there's many other examples of where you look at evolution of networks. Where evolution of networks are very interesting is especially if you think about this with diffusion of information and diffusion of certain practices. For example, in this case, you can look at evolution of industries over time, where every dot is a different company. Companies can be of different types. And you can now study how kind of collaborations and business relationships between companies are evolving over time. This is just examples of these types of networks. Then, right, like you can take this data that I had on the previous slide, but you can even further separate it out, let's say, in different industrial sectors, and then you can plot or try to analyze these networks over time, where again, edges mean alliances. And you see how for certain industries, they kind of go through very different patterns. In some, alliances form and get disbanded. In others, these alliances seems to persist. For example, up here, you see that there seems to be this kind of big alliance where everyone is a member of, and then there is the periphery, and then kind of over time, the biggest alliance kind of breaks down, but there's a lot of kind of small alliances. Similar seems to be happening here, but then this alliance network totally shatters. While, for example, I know in medical supplies, again, different patterns are observable, right? And these are right now very interesting and nice visualizations that give us a lot of ideas of what might be going on and how could we capture and characterize that behavior. This is collaboration structure of academic institutions. and the community structure is indicated by the color, so basically who's strongly collaborating with whom. And again, there is a temporal component between these networks over time. Yet another example of an evolving network, and I have the last one. This is these are the components of the Apple's inventor network over a 6-year period. So basically, ties here correspond to people co-writing a patent together. And these are, let's say, all the people from Apple who have published patents. And this is the temporal component. And you can see how the network is growing, getting bigger, right? And the size of the node measures their total number of collaborations or patents they have produced. And then colors mean different technology areas or classes. And again, there is very interesting here, the colors seems to be very clustered, but as time goes on, you can see that these colors are less clustered, so it means that these patents, these collaborations seem to be more interdisciplinary, at least at the Apple company as the time goes on. And you know, Apple is interesting because, you know, this was probably the best time for Apple, and Steve Jobs was around, and good stuff like that, right? So just more examples of how can you think about evolving networks. So now what are we going to do in this class today? We are going to talk about ways to study evolving networks at several different levels. We'll talk about how networks evolve at the global macroscopic level. We will talk about how networks evolve at the this kind of intermediate scale of resolution. We will talk about how network motifs can capture evolution of networks. And then we'll also talk about how networks can evolve at the level of node properties. And the way we'll do the lecture, we'll first do number 1, then we'll do number 3, and then we'll do number 2. Okay? So the way you can think about it at number 1 is like, how does the entire network structure, the property of it, how does it evolve over time? At number 2, you are asking, how are these network motifs, little substructures, how are they being created and how they appear over time? And then here at the bottom level, you can be basically asking, how does the importance of the node in the network change as the network structure is evolving, right? So that's a node level question. That's a question for groups of nodes. And the top is question for all the nodes in the network, right? So that's how we want to think of this, right? So as I said, at microscopic, we are asking about individual nodes. At mesoscopic, we ask about groups of nodes. And at macroscopic, we'll be asking something about the property of the entire network. So what I want to show you first is this notion of macroscopic evolution of networks. This was very fascinating. So actually, this was my first paper I published as a PhD student. This was in 2004. And I'll show you basically my first project as a student. Okay? So here was the idea. The question was, how do networks evolve at this global level, right? What are some global phenomena of network growth? The way you could think of this is to ask basically, how are statistics of the network change over time? And I asked myself 2 very simple questions at that point in time. I asked, you know, what is the relation between the number of nodes and the number of edges over time? Like something super basic, right? And then the second one was, how does the diameter of the network change as the network grows, right? And then kind of as a follow-up, we also asked, how does the evolution of the degree distribution, how is that, right? How does the degree distribution of the network change over time? Okay? So these are, let's say, the 3 questions, and they are very empirical, but the question is, does this persist over different classes of network, and can I think of whatever we will discover as some kind of universal laws of how networks evolve? That's kind of the goal. The goal is almost like, can we do some kind of physics of networks? What are the basic laws? So here is one question, right? So if you say, at some given point in time t, I have n nodes and I have e edges. Now imagine that, I don't know, at the next time point or sometime in the future, the number of nodes will double. The question is, what will happen to the number of edges, right? So what's the number of edges when the number of nodes doubles? Or, you know, whatever. Number of nodes grows by 10%. Does the number of edges also grow by 10%, right? Do you have any thoughts? Do you think it will be less? Do you think it will be more?
I mean, if it's going to be very similar to what you had, then the full copy of the network will be double, and then edges across the gap will be more than double.
Okay, interesting. Okay, great. So you think it will be more than double. Okay. What do others think?
Same reason.
Oh, okay, good. It could be less, right? Like, because this would mean as network gets bigger, everyone gets more and more edges. So we'll just be swamped in edges, right? So maybe it is actually less than 2 times. The other option is if you have a process that grows and every node creates k edges, then why shouldn't it be just times 2, right? If nothing changed, the thing is just growing, nodes are added, each node creates a certain number of links, they should be able to maintain that number of links, so it should be 2 times 2. If the number of people grows, the number of connection grows, right? And I would actually argue that it's not clear why the number of connections should grow faster than the number of people, right? If there is, 10 billion people on the earth, does this mean that we'll have more friends? It's not clear that that means we'll have more friends, right? So it's a good question. So the question is what happens? And you were in some sense right, because it more than doubles, it turns out. And it doesn't just more than double and that's it, but it follows a very specific relationship, something that is called densification power law. So let me explain how this is, how you can now do this, right? So the question is, what is the relation between the number of nodes and number of edges over time? And the first guess, and what was in the literature at that time, was this hypothesis of average, a constant average degree over time, right? So basically, every person has 10 friends, so if number of people doubles, the number of edges double, but the average degree remains constant over time. As I said, this is not what you see in empirical data. If you take different networks, for example, the network of routers on the internet, or the citation networks, and every dot is a network at a different point in time. Every network has a number of nodes on the x-axis and number of edges on the y-axis. And if you plot this now on logarithmic scales, it will look like a line. And if you fit a straight line to it, you will have a slope that is non-trivial, like 1.1 or 1.6. Okay? So what does this mean? This means that the number of edges at a given time is proportional to the number of nodes at that given time, raised to this exponent a. And if the relationship would be linear, then the exponent a should be equal to 1. Okay? And then if you think about it more, the exponent a can be only between 1 and 2, right? 1 means you maintain the degree. Less than 1 would mean the average degree is decreasing over time. And 2 is the most you can do. The reason why 2 is the most you can do, because this means the number of edges grows quadratically with the number of nodes. And that's how quickly the adjacency matrix grows, right? You cannot increase the number of nodes cubically, because the number of possible edges only increases quadratically because of the adjacency matrix size, right? So this means that A will be, let's say, between 0 and 2. It turns out that it's 1.6, 1.2. So it's bigger than 1. So it means that edges at a given time is node raised to some power a, and that power is non-trivial, and it's bigger than 1. So it means the number of edges is growing faster than the number of nodes, which means that the average degree in this network is growing over time. And that's why it's called the densification power law, because the network is getting denser. There is more and more connections in there. So that's the first empirical observation, and I could show you a list of many other networks where this holds. So there is the following thing, right? Like basically the observation is that the number of edges grows faster than the number of nodes, or that average degree is increasing over time. The relationship is the following equation. So nodes raised to the power alpha, power a, is the number of edges. Or another way you could say is that log number of edges divided by log number of nodes is a constant, right? If I take logs on both ends and divide, I get that. Yes?
So when you talk about the number of nodes growing over time, especially in observational data, are you assuming that if a node is there at time t, it's going to be there at time t plus 1, or could it be different nodes coming in and other nodes going out?
Great question. So actually it's both, right? So in a citation networks only grow. Kind of old papers don't die. In the network of internet, servers come and go. So what we actually did that's an excellent question you're actually asking. So here, this is not time, but this is size, right? So we took all the snapshots of the graph of autonomous systems, so basically of the internet topology, and sorted them by size. And now this is size versus edges, and here is really time versus edges, because this is just kind of growing over time. And I think these are monthly snapshots of a archive citation network from the beginning of archive till some time, right? So excellent point. So basically the answer is both. All right, great, thank you for that. As I said, A is this densification exponent. It will be less than 2 because you cannot grow more than quadratically. And if it's 1, it's the constant degree. It could be even like if the degree would be slowly decaying, it could be actually less than 1, right? But 1 would be linear growth, 2 would be quadratic growth, and in reality, we empirically observe is something in between. But it's non-trivial. It means it's greater than 1. So that's the first interesting empirical observation about these networks. So here's another one that is interesting, right? So we remember earlier in the lecture number 1, lecture number 2, we talked about the random graph model, and we talked about what is the diameter of the random graph on n nodes. And we showed that the diameter of a random graph grows logarithmically with the size of the graph, right? Which makes a lot of sense, right? If I have a graph on a few nodes, I have some diameter, and I take a bigger graph, the diameter will be bigger, right? It's like if I take an object, and I measure how big it is, and now I take a bigger object, it will be bigger. So it should have bigger diameter, right? Actually, what it turns out is that that's not the case. Okay? So this is kind of super counterintuitive. If you plot or if you measure the diameter over time, what you find is actually shrinking over time, right? This is, again, the same internet graph, and this is the citation network. And you see how it's shrinking over time, okay? Now, of course, you will say, how exactly do you do this in practice? There are two things. One is that you wouldn't take the diameter as the longest, shortest path, but you would take the average or something that is more robust. I think here we took the 90th percentile. And then what if the graph is disconnected? Many times you have a lot of small connected components, but they are small, so you just focus on the big one. And that's how you do this in practice, right? So what's the observation? The observation is that the diameter shrinks over time, right? So even though the network size doubles, the diameter goes, here from 4.8 to 4.6. And here, this is the archive citation network over, I think, like 16 years or more. It goes from 10 down to about 5. Yes?
Can you explain it again? Like, why don't we take the maximum diameter, like the...
Oh, this is just how do I quantify diameter. And how do I operationally measure it. And the way the diameter is mathematically defined, it's the longest, shortest path. And the problem with that is that it's very fragile metric. You can have just something like sticking off, some tentacle sticking off, and it will totally throw you off. So you don't want to measure the maximum, but you want to measure something close to the maximum. So what you really do is you do something that is called effective diameter. And effective diameter is defined as the 90th percentile of the shortest path distribution, right? So it's kind of the maximum, but it's a bit less so that the outliers don't make your metric too fragile. So that's the intuition. So here, what I was measuring was the 90th percentile of average shortest path length distribution between pairs of nodes. All right? Yeah? Yes. All right, great. So that was the idea. So now you can be like, wow, this is so cool. But you can say, really, Jure, you are silly. Of course we know why this is happening. So why should you be unimpressed?
Because the networks get denser and denser over time. So
Great, exactly, right? So you should be, in some sense, you should say, like, of course, the number of edges is growing over time, and of course, whenever you throw in one more edge, you make the diameter a bit smaller, right? So what I showed you on the previous slide may mean that the diameter is collapsing just because there's more edges, and there's nothing, you just measured the same phenomenon twice, right? So the question now is, do I have two different phenomena, or am I measuring the same phenomenon twice, right? The densification, and this is just a consequence of densification. So here's one experiment that you can that we did to show that densification is not enough. Okay, so so you can ask, okay, how would I evaluate, is densification enough? So here's the simplest way, is to say, is shrinking diameter just a consequence of densification, right? And the way we did it was to say, let's give an answer by simulation. So the idea was, let me generate random graphs that densify. So I will show you random graphs of different size, and each random graph with n nodes will have n to the 1.5 edges or something like that, right? So it will densify, okay? And let's measure the diameter of it. And if you do that, this is what you get, okay? So here, densification exponent that I was using to generate these graphs is 1.3. So my random graphs are getting denser. So if the densification would be the sole contributor to the shrinking diameter, then I should see the thing going down, but I don't, right? So what do I conclude? I can conclude that densifying random graph has a increasing diameter. So this means that there is more to shrinking diameter than just the densification. There must be some other ingredient, because here the densification itself is not enough, right? So there must be something else. All right? Yes?
What if you did the same thing, but instead of Erdos-Renyi graphs, you generate basically power law graphs?
Great question. So that's exactly what I asked next, was like, is there something else that is special? So maybe Erdos-Renyi is too naive. So let's say we would say, what if we generate random power law graphs that densify? Okay, so the way we asked the question was, what could explain is it the degree sequence that is changing over time, right? So it's not only the densification, but it's also how nodes gain degree as how they gain edges over time. Okay, so how would you do this? The way you would do this is the following. You would say, let me take the real network and let me measure its diameter over time. And now let me take a random network that has the same degree distribution as the real one, right? So now I'm saying I will have a sequence of networks, they will get bigger, they will densify, and I will compare a real network to a random network that densifies and has the same degree distribution, degree sequence, okay? Yes, okay? So let's see how will this look like, right? And here is how it looks, okay? So this is time. Now this is the archive paper, the archive citation network. Red dots are diameters as a function of time, and then the blue dot is the blue line is the diameter of the network that has the same number of nodes, the same number of edges, and the same degree sequence as the red dot. And you basically see that the blue line follows the red dots, like super well. Okay. So what do I learn from this? From this I learned that densification plus the evolution of the degree distribution of the degree sequence leads to shrinking diameter. Okay? You guys convinced? Yes?
Are we sure that the densification does it? Like, would just the degree sequence also do it?
Great question. Would just the degree sequence do it? So we'll ask next. All right, anyone else, anything? All right, so let's now go and see what has happened to this guy, right? Like what is happening to the degree sequence? Can I model it? So the question is, how does the degree sequence evolve to allow for densification? And there are two ways how the degree sequence can evolve. The first thing I should say is that, what I should say is degree sequences are heavy-tailed. They follow a power law degree distribution. And these power law distributions are funny because you can have a power law degree distribution or a power law distribution that has infinite expectation, which means you have a distribution when you ask what is the expected value is infinite. Or another way to think of it, you have a distribution from which you sample data, and the more data points you sample, the higher the average will be. Okay? And what you can prove is that the degree distribution that has the exponent between 1 and 2 is a degree distribution with infinite expectation. And this means that for these types of degree distributions, the densification will be 2 over gamma, where gamma is the slope of the distribution and has to be between 1 and 2. Okay? So what does this mean? This means that you can have a degree distribution that maintains its shape, but because it is so heavy-tailed, as more nodes arrive, more heavy hitter high degree nodes will come, and that will push the total number of edges, the sum of the degrees, to increase over time. Okay? To show you or to say, right? So the consequence of this is that power laws with exponents less than 2 have infinite expectations. So by maintaining a constant degree exponent alpha, or constant degree exponent, gamma in our case, the average degree will grow. And to show you an example of this, here is a email network, degree distribution of the email network. It has this straight line shape. If you ask what is the slope of this line, it's 1.8, and this 1.8 is maintained over time, but the network is still densifying because the degree distribution is very fat. There is kind of so much mass here in the tail is that the high degree nodes keep increasing the average degree, even though the shape of this remains constant over time. Yes?
What is the topological interpretation of the degree exponent? So I mean, like, we can see it's like the slope of this degree distribution, but like,
what does this mean?
Yeah.
So this means this is the node degree, and this is the number of nodes of that degree, right? Aha, and gamma is the slope, of this thing, and essentially the way you can think of it, the bigger the slope, the less mass you have in the tail. So the fewer outliers you have, and the smaller the slope, right? Closer to 1 it gets, the more outliers you have here in the tail, right? And these distributions are fundamentally different than this kind of exponential family distribution, Gaussians and so on, which if you would plot them on a log-log scale, they would kind of look like this. They would just finish, right? Here, this thing has a lot of mass in the tail. So you have these basically super high degree nodes, and most of the nodes have very low degree. Yes? Great. I'm sorry. I did not. It's a good, how to say. There are reasons why this is the case, and maybe it's my mistake that I flipped the order of 2 lectures and I didn't really explain this. But the fact is, and I'm happy to point you to the place where this can be explained, is that basically for power laws, for these types of distributions that look like straight lines when plotted on logarithmic scales, their expectation will be infinite if the slope of this line is less than 2. Or if it's between -1 and -2. And then if you make it, if you make it less than -2, so let's say -3, then the expectation is finite. It's a fact that you can, if you write down the power law distribution, say compute the expectation as a function of the exponent, then you find out that in this regime, the expectation, the first moment is infinite, but the second moment, variance, is also infinite. For exponent between 2 and 3, the expectation, the first moment is finite, but the variance is infinite. And then, between 3 and 4, the first 2 moments are finite, but the third moment is infinite. So this is how these distributions look like. I it's a good point, and I should have had a better explanation. And it turns out that many real-world phenomena are distributed this way. If you look at wealth is distributed this way. If you look at number of people with a given surname, is distributed this way. If you look at sizes of cities, it's distributed this way. If you are looking at the magnitude of earthquakes, it's like this, right? So and this just means that extremes can be very, very big, right? If you have infinite variance, this means a huge earthquake can strike at any point in time, right? I'm not calling it, but that's the point, right? All right, so thank you, great questions. I'll provide more background on this. Okay, so that's the first thing, is if these power laws are funny distributions, if you are in this range, your expectation will be infinite, so which means it will grow with the number of samples. And if you look at some network, some types of networks, they actually maintain the same degree distribution, and they densify because of the shape of the distribution. And then there is a second one, that the option 2 is that this degree distribution evolves over time. One can derive how the degree distribution should evolve, but essentially this is the number of nodes, and x is the densification exponent. What you notice here is that is the following. For example, the way you can think of this, to give you an example, here is a citation network that we were talking about before. It has kind of this type of degree distribution. You can again estimate the exponent of this thing, and if you plot the exponent over time, the exponent is decreasing. So what this means is the distribution goes from something very with not too much fat tail to something that is less fat, right? And by kind of moving that way, it's pushing more and more of the degrees towards higher degrees, and that's why it is densifying, right? So basically, this is saying that the degree distribution is getting flatter over time, right? The exponent is getting smaller. Yes? No? Is it clear what I'm trying to show here? So what I'm trying to show is I take multiple snapshots of the network, and for every snapshot, I ask what is the slope of the degree distribution. And I'm showing that early on, the slope is, let's say, minus 3.5, then it's minus 2.8, minus 2.7, and so on. Right? This means that the degree goes from being very, very steep to getting shallower and shallower. Right? This is, at the end, y equals x raised to the power of minus this. So the smaller it is, the shallower, kind of the slower it decays. And because of that, the average increases. Here is the average. Here is the expected value of a power law distribution with a given exponent. It's exponent minus 1 divided by exponent minus 2. Right? So as the exponent gets smaller, the average will increase. Yes?
I just saw the answer to my question on the slide, so I was asking, it seems like it's converging towards an exponent of 2.
Exactly.
And then I saw that it's also on the slide.
Exactly. Exactly, right? As it's converging to the exponent of 2, it's basically converging to this infinite mean regime, and then it will stay there. All right. Good. So this is what I wanted to show you in terms of what is happening. So what is happening is networks are densifying and diameters are shrinking, and the reason for that is the way that the degree distribution is evolving over time. Either it's being basically having the distribution is constant, but has this weird property that it's getting denser because of the property of power law distribution. Or the exponent is evolving according to a given shape, and that gives us densification. So that's what I wanted to show. So now what I wanted to show is what would be a good model that would generate these networks. Yes?
I have a question. So does it mean that if the exponent is between 1 and 2, that it tends to not change over time?
At least that's what we see empirically. Yes. It doesn't have to change. It will still densify. Yeah. All right. So here's the model that allows you kind of to empirically generate networks with these types of properties. The model is called the forest fire model, and the idea is the following: the the intuition for this model came from the from a party, and the question is, how do you get introduced to new people at the party, right? When I was a young student, first time in US university, I needed to be introduced at parties, so I observed how that is done, right? And the way that is done is the following, right? So how do you meet friends at the party, right? Or how do you identify references when writing papers? Here is you without any friends. So if everything goes well, you meet someone, and what do? They introduce you to their friends, right? And then you make connections to them. And over time, you will make more connections. And that's the idea for this forest fire model, where idea is that the new node will come. It will somehow select the ambassador node, the W. And now we will try to basically, in some sense, start some kind of forest fire that will spread over these edges, and wherever the fire will spread, we are going to create connections to those people. And as the fire spreads, this we will create connections to other people. Okay, so the idea will be that somehow, now that we have selected the ambassador and kind of linked to the node, we will somehow decide which of the neighbors of W get the fire, maybe here the fire does not spread, but here we decide to spread it. So we will connect to this node as well. Then maybe here we again decide whether to spread the fire over these edges. Maybe decide to spread it here, so we'll create an edge. Decide to spread it here, create another edge. Maybe we decide to spread it here as well, create another edge, and then keep deciding where to spread it or not until the fire dies. And this new node will link to everyone who the fire burned. Okay, that's essentially the idea. It's a very simple iterative process, basically a network evolution process, where at every step node comes, selects an ambassador, we run this forest fire process, whoever gets burned, we create links to them. And then the new node arrives, and so on, right? So this is more like, how do you identify references, right? You say, I want to write a paper, I find something similar, I see who this paper cites, I follow this reference, I decide now I'll cite this paper as well, I follow the references of this paper, and so on and so forth. And then when I'm like, have too many references, I stop, right? And then the next paper comes. So that's the intuition. So how exactly you do this is the following. You have two parameters. You have what we call the forward burning probability and backward burning probability, because you can follow the references forward, or you can follow the references backward. This would be for directed networks, where the model operates the following. At each turn, a new node arrives. Uniformly at random, we choose this ambassador node W, and then we flip two coins sampled from the geometric distribution of parameters with parameters P and R that determine what number of in and out links of W we want to follow. And then we select that number of in and out links of W and spread the fire along those links. And then the fire now spreads recursively to those nodes. To each node where the fire spreads, we again flip the two coins to know how many out links to follow, how many in links to follow, and we continue this until the fire dies out, and then a new node V will link to all the burned nodes. And that's how this model will work. Okay, that's the idea. And as I showed before, here is the simulation of the model. Here are basically more details, but again, it's operating in iterations. At every iteration, a node will arrive, select the ambassador, and then here we start this recursive process where we determine how many out links, how many in links to burn, spread the fire along these links, and then continue the fire at the endpoints of those links, and we keep doing that until either we burned the entire graph or the process stops, which means that these coin flips would say don't burn any links, or the node has no links, or something like that. Okay, that's essentially the idea. Right, how the works. V arrives, selects W, samples the in and out number of in and out links. Then we select the two outgoing neighbors and one incoming neighbor. Let's call them this way. And now we repeat the same process independently for each of these nodes. And then whoever got burned, we create edges to them from V. That's the idea. So now the question is, if you set some parameters, do you see densification? Here is the number of nodes as a function of time. Here is the number of edges. And here are dots are the graphs. And if you plot this on logarithmic scales, fit a line, you get a very nice straight line here with the exponent of 1.3. And then if you also plot the diameter as a function of the number of nodes, again, you see how basically the diameter is shrinking. Yes?
In the previous slide, why do you want to connect with the inlinks of W? Like, can't we just simulate the forest fire model with just connecting to the outlinks of W and then like repeating the process for those?
So the reason why you could also just do outgoing. We actually decide, but the problem with doing the outgoing is that if you just do it down, then you are just creating a DAG, right? You are always just kind of linking just downstream, and we wanted to be able to link upstream as well. So that's why we have both processes, the kind of the downstream fire, but also an upstream fire. That was the intuition why we decided to have both. Okay. So this is one example, here is another thing is does the model also generate the realistic degree distribution? This is the in degree, that's the out degree, and again you see how it follows a straight line when I plot it on logarithmic scales. Yes.
For the in degree distribution, you take both the parameters P and R. Like for the out degree distribution, there is only P. The geometric distribution.
Yes.
So like, why do you want to take the parameter from the out degree distribution as well?
You essentially need two parameters, and then the question is, how do you parameterize the thing? One way to parameterize is to say, I have two different things. Another way is to say, this is the base, and the other one multiplies it as some kind of a factor. And at the end, it's the same. You could have two separate things, or you take one, and then for the other one, you take the first one and multiply it with the second one. It's just a different way to think about it.
Okay, so by using one factor in both the things is common, you kind of regulating the effect of...
Exactly, then you have a way to think about it. You say, the forward burning is that, and now what fraction of the forward burning power is the backward burning power, right? It's easier to think about. That's the sole reason. Good question. All right, good. So we have this, we have that. Now, of course, you can ask, how big is the parameter region where I get this notion of shrinking diameter and densification? And here is the computational experiment to do that, right? Here is the forward burning probability, and here is here's the value of a given statistic. Here we actually, I think we select the forward burning probability, and then the backward burning probability is some function of this, some constant times this. And then and here is, we are burning very little. Here we are basically burning everything. This line, the dotted line, is the densification. When we are not burning anything, then essentially, if the forward burning is 0 and backward burning is 0, then we are just creating one link per node. So no densification. Okay? And then as we are increasing this parameter, we need to increase it quite a bit. And then the densification happens, and then all of a sudden it gets all the way kind of up to 2. Which basically means that from then on, whenever a node comes, we just burn everyone, right? And we are essentially creating a complete graph, so the average degree is increasing quadratically with the number of nodes. Okay, so to get densification, we have a relatively narrow region of the parameter space where this happens. And then this is the diameter, where the way to think of this is we fit some way to characterize whether the diameter is increasing or not. And if it's above this line, the diameter is increasing. If it's below, it's decreasing. And again, you see that in this regime, when we get some interesting densification, also the diameter of the graph tends to decrease, right? Here, it's slowly increasing. And then if it's at 0, it means it's constant. And again, why is it constant here is because we are creating a complete graph, right? Every node links to every other node, so diameter will be constant, it will be 1. We are creating a complete graph, so everything from here on makes total sense. Here, we are essentially creating a tree, so the diameter is increasing over time, right? And here is this narrow region where we have both we have densification and shrinking diameter, right? So there is some relatively narrow parameter region where this happens. Okay, so that's what I wanted to show about the macroscopic part. Are there any questions? Yes?
Go back to the last slide. Why does the diameter increase when the forward burning probability is like going from 0 to 0.4?
So why is diameter increasing here? Because if the burning probability is small, then just think of this endpoint here. This means that whenever a node arrives, it selects an ambassador, but then no fire happens. So this means essentially I'm creating this tree where every node has one edge, one outgoing edge, right? So the diameter will be increasing because I'm just creating a tree. And it won't densify because every node has exactly one outgoing edge, right? And then here diameter is constant because I'm creating a complete graph. So everyone's connected to everyone, the densification is maximum, and right? And you know, the reason why does it go above 2 there a bit is just for the empirical reasons, right? Because, I don't know, imperfect fitting or whatever you want to call it. All right? Good question. Great. So let us continue. So now I want to talk about this notion of temporal networks and then tell you about some measures of nodes of basically give you a generalization of page rank to dynamic networks. So here's the idea how we'll now think of this. So far at the macroscopic level, we only looked at this kind of snapshot. We said for every day, for every month, for every year, let's create a snapshot of the network. What we will do now is we'll say, can we be more faithful to how nodes and edges are coming and leaving? So we will define this notion of temporal networks, where a temporal network is a sequence of static graphs over the same set of nodes. And each temporal edge has a timestamp, is a timestamped ordered pairs of nodes. So I know node time, where ti is the timestamp at which the node exists, right? So the way I could think of this is, if I have the network, you know, this edge AC existed at time 2, CD existed at times 1, 2, and 3, CE only existed at time 1 and existed at time 3, but at time 2 it wasn't here. That's what we would like to capture. And these edges we will call temporal edges because they can exist or not exist. Okay? And now we can think of temporal networks as a sequence of static graphs where every graph has the same set of nodes, and then the edges change, right? So what I'm trying to say is that this graph here on the top, if I create a temporal network out of it, one representation would be that now I have 3 snapshots of the same network, but edges change between different snapshots. Again, for example, edge CD is here all the time. CE should be here at time 1, not here at time 2, but again here at time 3, right? So that's one way to think about it. That's another way to think about it. I'm just trying to give you some intuition how to define these things and how to think about them. What would be examples of these types of temporal networks? You can think of communication networks like email, phone calls, face-to-face. You can think about creating proximity networks, which is who is physically close to whom. These types of networks are very important for disease transmission, right? So you could think about how are people in the same hospital rooms? Do they meet at conferences? You know, do you have animals meeting each other in the forest and so on? You can think of this also as transportation network, where in transportation networks where trains or planes fly, and also in biology. This is a communication network over different days. I think it's at a given I think it's at a university somewhere on the East Coast, where you basically have a set of nodes and you see the communication between them. And you see that there is a lot of communication on Monday, maybe even a bit more on Tuesday, Wednesday, Thursday, Friday quite a bit, Saturday and Sunday people don't do email, right? Just if you plot that out. Another example is this is two different networks of people's physical proximity, where these are the time slots, I think, when people were let in, and this is now on 2 different days. And you can see how essentially this network is kind of time ordered, right? Is who's hanging with whom, and here is this edges show this is the longest path in the network that defines the diameter, and I think they just visualized it to try to show what's kind of the backbone of the network. But that's another way to think about this. So now that we have this notion of temporal networks that I just defined and showed you kind of 2 examples of them, we can now start thinking about how do networks evolve at this microscopic level? How do the nodes change over time? So what are we interested in? What are some kind of local node-specific phenomena in the networks as networks evolve? So what we will talk about is how do we define paths and walks on temporal networks, and how can we then extend, for example, the notion of PageRank or some kind of node importance to temporal graphs. So that's the second topic I want to talk about. Okay? So now we need to define basically this notion of walks and paths that we defined on simple graphs and extend them to temporal graphs. So the way I'll say a temporal path is simply a sequence of edges so that edges obey time, right? Like whenever I cross an edge, the next edge I cross should happen after the edge I traversed. And that's essentially it, right? So if I have now this temporal network here, then, for example, a sequence of edges 5, 2, 2, 2, 1, together with a sequence of times would be a temporal path, right? Why? Because I go from 5 to 2 here, and then I do nothing at time 2, but at time 3 I can go to 2 to 1. So this is a valid temporal path, right? So 5, 2 to 1 is a valid temporal path because I go from 5 to 2 at time 1. Now I wait 2 steps at 2 time points at position 2, and then I go from 2 to 1, and I completed the path. Okay? So this is now a valid temporal path. Notice that when I come into the node, I can wait there as long as I want. I don't have to move in the next time. I can wait there. That's why this is interesting. So now, the first thing you can then define is this notion of temporal shortest paths. And the way you do temporal shortest paths is to basically generalize Dijkstra's algorithm. And all you are doing is to say, when you come to the node, you can only go out of the node by the edges that happened after you came in. So I show you a lot of pseudocode here. This is just a shortest path algorithm, but the way to think of this is that basically on the input I will get the source node, I'll get the target node, I'll have the time at which the query starts, so the time at which I, let's say, want to start at the starting node, and now I want to calculate the distance, the shortest temporal path that connects NS to NT. And essentially, the way we want to think of this is to have this iteration. Here we are setting the distance to all the nodes to be infinite. Here is where we start the walk, start the path. We insert the starting node into the priority queue, and then until the priority queue is empty, we iterate. But essentially, what we are doing is to say, out of the priority queue, get me the node that has the shortest distance. If that node is the target node, then return me the distance. Otherwise, let's go over all the neighbors V of this current node U. And here is what we are doing. What we are doing is to say, the time the start time of the edge has to be less than q sub t, and q sub t has to be less than the end time of the edge, and the distance to u plus the weight or the length of the edge we are currently considering e has to be less than what was the shortest path to that node v so far. And if that's the case, we update the distance, and then we insert the v and the distance into the priority queue, and so on. The only thing that is different here from the traditional shortest path algorithm is this part, where we are basically checking the time of the starting time of the edge and the end time of the edge, and say, is my query time, is this inside that interval? And the rest is kind of standard Dijkstra's algorithm. I want to show you an example of how this looks like. Imagine I have a sequence, so basically I have a graph that evolves over time. Here it is at 5 different time points, 1, 2, 3, 4, 5. And what I'm interested in is the shortest path between A and F. And at time 1, the shortest path is this. For example, at time 2, the red edges are the shortest path, right? Because the length is 50. At time 2, I misspoke. The red edges are the ones that appear, and the shortest path is now that, right? So 3 plus 3 is less than 7, and 8 is less than 4 plus 6. So that's now, so the shortest path is A, C, D, F. Then at next time step, let's say these two more edges appear. So now the shortest path is here, here, and then up and down. At the next time step, let's say assume this edge 7 disappeared, but these two new other edges were added. So now the shortest path goes up here, and its length is 12. You know, at this next timestamp, the weight of this edge changed, but the shortest path will stay the same, right? And the algorithm we have there will basically allow us to identify shortest paths and how they move as the network structure evolves. Yes?
So are we running this once for the entire set of graphs, or are we running it for every?
We would run it for a given query time. We are running it only for a given query time, right? We want to say what's the shortest path in the network at this given time, right? And that's here I'm saying, if this is the query time, the edge has to be valid, right? The starting time of the edge and end time of the edge has to be in between the query time, right? So I'm basically saying, what's the shortest path at a given time? So the query is source, destination, and the time. Great. Actually, thank you for asking this. Yes?
So query time is a point, not an interval.
The query time is a point, it's not an interval. So running this with t equals 4, that's the path I get. Running this at t equals 3, this will be the path I get. So one option would be that you have the temporal network represented as a graph where every edge has a time, starting time and end time. This, in principle, could be something more complex if you have now several little intervals when a given edge was active. Another option would be to say, let me first just materialize the graph of all the alive edges at a given time, and then run simple Dijkstra. And here we are trying to do we are doing the two things at the same time, which means we don't have to rerun Dijkstra. We don't have to materialize the graph, right? So we save materializing the graph. So that's the first thing I wanted to show. And why did I want to show you this shortest path algorithm? Because there is this notion of closeness centrality. And closeness centrality is a measure how close is a node to any other node in the network, right? So if you are very central, then you have short paths to everyone else in the network. And if you are non-central, if you are on the periphery, you have long paths to everyone else in the network. So the notion of closeness centrality tells you whether the node is kind of in the middle or is on the edge, right? So now we are defining this notion of closeness centrality for a given node x at a given time to be simply the sum 1 over the sum of the shortest path lengths between the node x and every other node y at a given time t, right? So this basically means, and now I can define this as a time series as I can change t, right? And this will tell me how the closeness centrality of a given node is changing over time, right? So for example, here, if I ask what's the closeness centrality of node A at time 2, then I would basically ask what is the shortest path distance between node A and any other node in the graph at time 2. Here are the distances. I would sum them up, do 1 over that, and this would be the closeness centrality. And the way why did I do it this way is because higher is better, right? So higher centrality, higher value of centrality means you are more central, right? So you have shorter paths to everyone else. Okay, that's essentially the idea. So I can use the algorithm on the previous slide, and now do this calculation. I could do it over all the nodes. I could select a subset, a random set of nodes, and run this. Then, of course, what's kind of the thing you also would have to worry in practice would be the following. For example, here, if I'm at time 2, then the distance to node B should be interesting. So the question will be, what happens to the shortest path if I cannot reach a given node? And what you could do is use some large constant or something to put in here to account for that. I think that's what they do. Okay, so that's notion of temporal closeness centrality. So now you are able to track the importance of the node as a function of time. Yes?
Because doesn't this become like computationally very expensive?
That's a great point. So you are saying it is expensive because you have to do kind of all pairs, shortest paths over all times. Yes, correct. How could you do it is that you'd approximate this using some kind of random sampling. That would be a way to approximate it. Good point. Great. Okay, so that's one. So now what I would like to do next is to talk about generalization of PageRank, right? So the idea now will be the following. Imagine again I have some temporal network. Then, for example, what I'd like to do is I'd like to model how does the PageRank of a given node change over time, right? And for example, if now here I'm looking at node A here in the center, you can see how early on node A receives a lot of edges. It gets one at time 1 and 2 and 3 and 5 and 6. But then at the second part of time, 10, 11, 12, it doesn't get any edges, right? So the observation would be that A initially receives many inlinks, and thus it should be considered important early on. But after some time, it does not receive any inlinks. So that means kind of its importance should diminish over time. So with this, let's see if we can generalize PageRank to this setting. Okay, so now what I want to do is, as I was saying before, we had a notion of a path. Now let's define a notion of a walk. A temporal walk is a sequence of edges such that the times, again, when we traverse the edge, are time obeying. So for example, 5, 2, 2, 1, 1, 5 is a valid walk, because again, I'm traversing edges one after the other, meaning that the times when I traverse the edges are non-decreasing or are increasing, right? Notice the way we defined it, that you could do 1, 2, 4, 2, 4 in this step, and then in next step you could, I don't know, wait till here and do 4, 1, 1, 2. That would be still fine, because you can traverse multiple edges in the same time step, given the definition. Okay, So that's the notion of temporal walk. So now we want to define a random walk on a temporal time respecting graph, right? And again, the idea is that the timestamps needs to increase along the path, right? So an example of from C to B to A and back to C is a time respecting walk, because I traverse this at 2, then at 7, then at 9. But for example, from A to C, I can only move at 9, but then from C to B, I would have to move at time 2, so this is not time respecting, because I arrived to C at time 9, and the edge 2 has already kind of happened. So this would be a non-time respecting walk. Here I'm making an assumption that the edge is alive only for one time unit, right? I'm kind of taking the interval and simplifying it to be, you know, this is alive between 10 and 11, and the next one is alive between 11 and 12, and so on, okay? Now that we have that, we can now start thinking about what are the probabilities of temporal paths. And what I'll do next is kind of, I'll introduce quite a bit of notation and thinking how to properly define this, but when we are going to compute this, we will use a different algorithm that will be simpler and won't be so computationally intensive than basically trying to implement this the way I will explain it. So kind of bear with me, and then we'll talk about the method, right? The way we can think of this is, what we want to do is we want to calculate a probability of a temporal path, right? So we want to say that we want to ask, you know, what's the probability of me going from U to X at time 2, given that I went from V to U at time T1, right? And my goal would be here to model this notion that the probability of transition should decrease as the difference increases, right? The bigger the time delta, the less likely I am to kind of take that step. So the way people model this is to say the transition probability from going from when I arrive to U at T1, and now I want to go from U to X via at time T2 should be beta raised to some power gamma, where beta will be between 0 and 1. So with increasing gamma, this will get smaller. And then how is the gamma defined? Gamma is defined as a set of all temporal edges from U during this interval T1 to T2. Okay, so I'm basically saying the gamma is the number of edges I was able to, or that I could have picked between the time I came in and the time I left, right? And the longer I have to wait, the bigger this number of possible edges will be, so the lower that transition probability will be, right? It's essentially saying there were all these kind of trains that went by and I was waiting for the right train, and the longer I wait, the less likely I am to take the one that came. Yes?
So I'm a little confused. What's the difference between temporal path and temporal walk?
Aha, great question. What's the difference between path and a walk? A path in a path you cannot visit the same node again. On a walk you can do you can be drunk and it's kind of fine, right? But in a path you are sober, so you don't go back. You don't return to where you started or whatever. So walk is a walk. Path is the nodes don't repeat. Okay. Great. So this is how we can think about these transitions, right? And the idea is, right, that the smaller values of beta increase the probability of walk stopping at high degree nodes, and right, because the smaller the beta will be, the faster this the decay will be. Right, so the less likely we are to take the edge, or the less likely we are to wait very long. And if beta would equal, for example, 1, then we would be willing to take any edge out of that node, right? While if the beta is small, this means the probability of taking the edge will decrease a lot as long as we stay longer. So the random walk will just wait at that given node and won't take the transition. So this is the notion of a transition probability and how it depends on time, and it will depend on time based on the number of edges that we could have taken, but we did not. So now here is the intuition, right? The intuition is that as time will go to infinity, the question is what will happen to this temporal PageRank, and the temporal PageRank will converge to the static notion of PageRank. Meaning, if you are able to use all the edges, then you will converge to you will basically compute the static version of the PageRank, right? So the way to think of this is that temporal PageRank will be like running a real PageRank on a time-augmented graph. And I will define this in the next slide, where basically we will connect graphs at different time steps via what we will call time hops, and run PageRank on this time-extended graph, right? So node u at time 1 will become a node that is defined by node and time in this new graph, and the transition probabilities will be defined as I said before, right? So you will traverse from node u at time 1 to node x at time 2, given that you came to node v that you went from node v at some time to node u at the next time based on this beta to the delta that we defined. Okay, so this is a complex way essentially of saying that I arrived at node u at time 1, and now I will exit node u at time t2. Okay, you will see why I write these things in this funny way. This is the way you can think of this is the following, right? If I have my snapshot of graphs, what I will do is I will connect the same nodes temporally, right? So I will connect A to B. I will connect, for example, A to C here, and I will then connect A to B here, right? Because why do I do that? Because the node A had, for example, link to node B at time 1, had a link to node C at time 2, and it had a link to node B at time 3, right? So now for every time comma node, I create a new node, and now I can, rather than thinking of these links appearing here, I can think of them as appearing between the node and the target, right? So this is how the links will look like, right? And I can now do this for all the nodes to create this kind of temporally augmented network. Is this clear? People see what I do, right? So essentially now this will be my full network, right? So rather than having, so I will have every node replicated as many times as there are time steps, and then edge will be simply edge that survives on a given interval will basically mean that nodes on those intervals link to each other. Okay, that is the idea. And now this is how we will think about this, right? And again, as I said before, for example, this edge will be here because this edge is alive here. But for example, the edge between E and C is alive also at time 3, so it means that E will link to C at time 3. So E at time 1 links to C at time 3. And now we can repeat this process to create this type of temporally augmented graph across all nodes and across all time steps, right? And now if I would run the PageRank on this temporally augmented graph, then now I would get a different importance, let's say, for node C at time 1 versus time 2 versus time 3, right? And this is essentially how this would work, at least conceptually. Do people have any questions? Right. So what we did, is we took the temporal graph, and now we created kind of a bigger network where we replicated our temporal graph as many times as there are timestamps. And then rather than saying an edge is alive in a given timestamp, we actually connected nodes across different timestamps. And this means that now we connected these temporal graphs this way as well. Yes?
Are we assuming that the edges are directed or undirected?
Are we assuming that the edges are undirected or directed? The way I'm doing it here, I wanna, so the cross time edges are directed. The reason why is that is, of course, I would make an edge from E to C, and then I would also make an edge from C to E, right? But I want these edges to be directed because of time-respecting walks, right? If you think about PageRank, I only want to go here. I cannot go back into the past. So these edges that go across time has to be only forward-pointing, right? That's essential. Yes?
Does this time augmentation also make it possible to include nodes that haven't been around for all time periods? Because I know that was like the original constraint was that we said the nodes have to be around for all time periods.
Yeah.
But that was because in like the non-augmented form, if you have a node there, it suggests that it was there, and if you don't have a node, it doesn't mean anything. But now you could include like a node that doesn't have versions of itself for time 1. Like it would just appear at like time 3 or something.
For example, right, this guy, for all intents and purposes, does not exist here. Yeah, right. So yes, you can have nodes coming and going, and essentially the way you can think of them as isolated nodes that are around all the time, and you ignore them. Right. That's an excellent point. All right. Anything else? Yes.
How as t tends to infinity, how does it converge to a static page?
Yes. Where did you see the claim? Let's see. This claim. So what this claim is trying to do is the following. I think what this is trying to say, as you unroll the time, the assumption here is that edges are arriving, but edges are never leaving. So what this is trying to say is that if you have the graph that only will grow, and if you think of this as temporal walk, then as these new edges will arrive, your final PageRank distribution will essentially become the distribution on will become PageRank on the final graph. So the way you think about this is as imagine no edges ever leave. So as you will start the random walk and you will keep iterating it, here the random walker will kind of be stuck here at the end, right? Because it can only make time forward and then it gets stuck here, right? So at the end, these guys, the PageRank scores of the nodes here will be the final PageRank scores. Does it make sense what I'm trying to say?
But why does it have to, the time shift has to go till in like?
No, what do I mean? Sorry, till infinity just means to the end, whatever is the end, the last step. Infinity means last step. Yes, that's a good point, right? So this is what I wanted to show you, and I want to show you just one experimental result. So for example, here is an experimental result. What these people did is they said, let's have this temporal notion of PageRank. Let's create this sample of 10,000 temporal edges, and then create another sample of 10,000 temporal edges and another sample of 10,000 temporal edges. And then let's keep adding these temporal edges in one after another. And let's measure how do the PageRank scores converge to the final graph that is here. And then the way you can think of this is these edges are coming in, and here is the final kind of static graph. And what is this showing is how is this correlating, or how does this relate to the final PageRank scores of the static graph. And what this is trying to say is that as you see very few edges, the scores are not so related with the final scores, but as you get to see more edges, they basically converge to the final PageRank values. And now you rewired the graph, you threw all the edges away, and you are now throwing in another set of edges, and again, as you throw in more and more edges, the scores converge to the final static graph you have at the end. And then you kind of reset the graph and so on, right? So this is to validate this claim that as you get to see more edges, as the edges are being added to the temporal graph, then the scores are kind of smoothly approaching the final static graph scores, right? This is in the case, this is just trying to say that as more edges are revealed, essentially this walk over the augmented graph converges to at the last step is the page rank on the final static graph, right? But in between, you get interesting behavior. And now you can, of course, trace the page rank score of individual nodes as the time goes on. So let me finish here. Thank you very much for all the questions. I thought it was, they were super good. It was super useful and super helpful. So thank you very much, and we'll see you next week.